All right, this is a video over day 34, part 2. So this is the back side of the worksheet, page 87 on the notes. And in a survey of 1,200 college students, 380 said they had tried smoking, and 800 had tried drinking, and 315 had tried both. We're going to make a two-way table to display this. So over here I'm going to put D, drinking. This will be the drinking. They've either done yes, well, we'll call it drinking, and drinking complement. And you could just as easily put yeses and nos. Okay, across the top, I'm going to put smoking across the top. And they've either S or S complement. Tried smoking or not tried smoking. Okay, so we've got, this is our the main part of our two-way table right here. And then we should have our totals columns going all the way around it. So it tells us that there were 1,200 college students. That's where 1,200 goes. That's the grand total. So 380 had tried smoking. So here's the smoking. 380 of those 1,200 have tried smoking. And 800 had tried drinking. So here's drinking. Go across. 800 had tried drinking, which means 400 had not tried drinking. So these add up to 1,200. 380 and 820 make 1,200, okay, who have tried smoking. The other thing we know is that there are 315 people who have tried both. So now we can fill these other ones in just by using subtraction. We can fill this one in by taking 800 minus 315, and you get 485. And you can fill this one in by taking 380 minus 315, that's 65. And you could get this one by subtracting these or these, and you get 335. So here's our two-way table all filled in. Now we want to find probabilities. So A, what is the probability that a randomly chosen respondent has tried neither? So the probability that they have, basically it's not tried drinking and not tried smoking. So drinking complement and smoking complement. So out of 1,200, okay, every probability that is not conditional is out of the total 1,200. So this is not a conditional, otherwise we'd know some information. So out of 1,200, how many have tried not drinking and not smoking? That's 335 out of 1,200. Okay, so the next one, what is the probability that a randomly chosen drinker, this is our given, has also tried smoking? So this is a conditional probability. Okay, this is a conditional probability. So I have to set this up, what am I given? What is the given? That's always the second part. I'm given that they have tried drinking, and I want to know the probability that they have also tried smoking. So using the formula for conditional probability, which says that the probability of smoking, knowing that they have tried drinking, is the probability of smoking and drinking divided by just the probability of the given event, which is drinking. Okay, I'm going to do this problem two ways. One way using the formula and the other way just using the two-way table. The formula is always the go-to though. So what's the probability that they've tried drinking and smoking out of 1,200? Okay, so the top and bottom of this conditional probability are out of the total. So drinking and smoking, that's 315. The probability that you've just tried drinking is 800 over 1,200. And so that, if you multiply by the reciprocal, you get 315 over 800. But the nice thing about having a two-way table and finding conditional probabilities is you can kind of do it in your head without using the formula, but only with a two-way table. So what you can do is you can say, well, the probability of smoking, knowing that they've tried drinking. The thing that I know is that they've tried drinking. So what I can do is go up here and say, well, that narrows me down to these people here, which is out of 800 now. Instead of out of 1,200, because I know this condition, I can say that it's out of 800. And of those, 315 have tried smoking. So the formula will work out the same as just thinking through it if you have a two-way table. All right, so part C, what is the probability that a randomly chosen smoker hasn't had a drink? Here is another conditional probability. Okay, this is another conditional. You have to read it carefully. It does not say and. That we've chosen a smoker. So what is the probability that we know that we have chosen someone who smokes and they haven't had a drink? So the probability of drinking complement. So I'm going to use my little technique from over here. I'm going to say, well, I know they have tried smoking. So that narrows me down to just the people who have smoked. So that's out of 380. Of those, the people that have not tried drinking are 65. And we're done. The formula would work out the same. Part D, what is the probability that a randomly chosen respondent has tried at least one of them? Now there's different ways to think about this one. At least one, okay, here's the first way you could think about it. At least one probabilities, okay, the probability of at least one of the two, of drinking and smoking and drinking, is 1 minus the complement of that, which is the probability that they have tried neither. So one way to calculate this would be to say, well, I already figured out the neither part up at the top. So to figure out this probability, I could take 1 minus 335 over 1200. And that would give us 865 out of 1200. Okay, now let's see if that works if we think about it differently. What is the probability the randomly chosen respondent has tried at least one of them? That would mean drinking or smoking as well. So that would be the probability that they have tried drinking or smoking. Okay, so how can you try drinking or smoking? Well, you could have just tried drinking, plus you could have just tried smoking, but we counted people that have tried drinking and smoking, so we have to take out the probability of drinking and smoking. So the probability of being a drinker is 800 out of 1200. And the probability of being a smoker is 380 out of 1200, minus the 315 that have tried both. Let's see, 800 plus 380 minus 315 gives us 865 over 1200. So either way works out that we think about it. All right, is smoking independent of drinking? Okay, this is a good problem. We've seen a lot of these in the last few days. If it is independent, we've got smoking and drinking are our two events. The way we prove independence is we say the probability of one given the other is the same as the probability of one of them. So I'm going to say the probability of smoking given that I've tried drinking would have to be the same as the probability that I've just tried smoking on its own. So first of all, we'll find the probability of smoking given that I've tried drinking, which we already found in part B. So that is 315 over 800. And just the probability of smoking, well, just the probability of smoking is 380 out of 1200. That's from the original information, 380 out of 1200. And so I'm just going to see if those decimals are anywhere near each other. And 315 over 800 is 0.394. And the other one, 380 divided by 1200 is 0.317. So basically we're talking 39.4% and 31.7%. And those are, to me, not the same. They're not within that range of 3. So I would say that smoking, okay, these are not equal. Not equal, which means they're not independent. Smoking is and drinking are not independent. Now, what would this mean in the real world? It would mean that if you smoke, you're more likely to drink, and vice versa. That one leads to the other. So now the next question, are smoking and drinking disjoint events? Meaning, can they happen at the same time? Disjoint events cannot, disjoint events cannot happen at the same time. So, can I smoke and drink at the same time? I can smoke and drink at the same time. So, not disjoint. Okay, that's the end of day 34. And now I'm just going to move right on and use the rest of this video to start day 35. So day 35, what we've got here going on is just more problems for review. We're just going to go over more. Here's data from a random sample of 100, we'll call it EHS students. Are being male and playing a sport independent? at East High. So we've got this information. We want to know if are being a male and playing a sport, are those independent? So I'm going to say, well, let's say what would be the probability of being a male given that I play a sport? And that would have to be the same as the probability of just being a male. I could do it a different way. I could do sport given that I'm a male and then the sport, but however I choose it. I just pick my two events, whatever I want to be what I'm finding the probability of is the same in both. So knowing here that I play a sport, in this case, knowing that I play a sport, that means that out of everybody, 30 out of 100 play a sport. So, well, basically 30 play a sport. So I'm narrowed to this right here. So 30 of people play a sport. So because I know I play a sport, I can say it's out of 30. How many of those are males? That's 16. So 16 divided by 30 is approximately 0.53 repeating. Okay, so what's the probability of just being a male? Well, just being a male is down here. That would be 48 out of 100. And 48 divided by 100, well, that's 0.48. So I would say that those are not equal. They're 5% apart. So I'm going to say that 0.53 repeating is not equal to 0.48. So playing a sport and being male are not independent. But they're kind of close, so it could have been. All right, so assuming the variables are independent in this population, how likely is it to get a difference this large due to sampling variability? Okay, well, what is sampling variability? Maybe I just asked the wrong or right 100 people. Maybe if I asked a different 100 people, I'd get like a 51 and 50% here for these. So maybe it's just my sample, and we're going to be looking at stuff like this in the next few chapters. So basically, here's a review. We're going to use a simulation to estimate this probability. So what we're going to repeat here, we are going to repeat select male and female students and ask if they play a sport. Okay, that's what we're going to repeat, step one. How are we going to model this? All right, so first of all, the way we model this is we have to assume independence, and that you always assume independence from, like when you ask each person that their answer is independent of the person before them. Okay, and so let's see, based on the information that we have, we are going to look at, basically we've got 30% overall play a sport. So if you look at the data from up here, overall 30% play a sport and 70% don't. So we want to see, could I have gotten this same information by random chance? So I'm going to use the data that I have for sport and no sport. 30% played a sport, 70% no sport. So sport and sport complement. So in order to model this scenario, 30% of the students playing a sport and 70% not playing a sport, I'm going to let like the numbers 1, 2, and well, I'm going to need like 0, 1, and 2 are going to represent play a sport. And then so 3 through 9 will represent no sport. And what I'm going to do for each trial is I'm going to select, well, how many of those in our original survey were males? Well, there were 48 males, so select 48 numbers from 0 to 9 to represent the males, and 52 numbers from 0 to 9 to represent females. And for each of those groups, I have to decide, like for each person, how many play a sport. So I'll base it, and so the response, I'm going to then count number who play sport.